right, good morning, everybody. Welcome. I hope you've had a chance to take a look at some of our upcoming events. We have a number of different trainings throughout October and November. Particularly what might be most interesting to you is our rotor dynamics analysis online workshop. We have 2 different sessions taking place November 18th to the 20th, as well as November 23rd to the 25th. Software is included in these trainings, so definitely if you see anything that you like throughout this presentation, it would be a good opportunity to kind of get your hands on the software. Next, our next webinar is going to be on cooled gas turbine simulation, coupling AxtremeNet and Star CCM. So it's a little bit more system level, but it'll be taking place on October 22nd. The page is already up and everything, so definitely check it out. All right, I'm going to leave this slide up for anybody that's having trouble connecting to the audio. It has the dial-in number as well as the webinar access code. And while I leave this up, just a couple of bookkeeping items. First, all attendees will receive a recording of this webinar early next week. So if you miss anything, don't worry about taking notes. You can definitely review this as many times as you want in your own time. Then the last thing that I want to mention is we'll have a Q&A session at the end of this webinar. So definitely if you're seeing the presentation and you have some questions, feel free to type them into the chat. We will address as many as possible at the end of the webinar. And any which we don't address, we'll follow up via email. All right, so the topic of today's webinar is rotor dynamics analysis for turbomachines with active magnetic bearings. Just to go over the agenda really briefly, I'll be giving a brief company introduction, and then I'll pass things off to my colleague who will take you through the meat of the presentation. So an introduction to the technology, operating principles, active magnetic bearings with Axtreme rotor dynamics, as well as a full case study with a 5-stage compressor which uses active magnetic bearings. The presenters are going to be myself. My name is Kimberly Squilante. I work here as a marketing manager, and my colleague Vladimir Martinenko. He is our rotor dynamics engineer here at Softenway. So just for a bit of background about us, we were founded in 1999 as an R&D engineering company specializing in turbomachinery component and system design. Originally, we had started out as a consulting company, but over the years, we had been using in-house tools to complete these projects faster, and we had a couple of clients ask about kind of what we were using in order to develop these projects. And with that in mind, we started to develop and commercialize a software called Axtreme, which I'll address a little bit later in this presentation. Currently, we support right around 450 customers worldwide. And to date, our business units fall into sort of 3 different categories. So first is Axtreme, our software platform for turbomachinery design, structural analysis, rotor dynamics, system level design, and so on. Next is our engineering services, and then finally we also have a pretty broad and extensive list of education options. So online training, self-paced video courses, as well as customized private trainings. For the most part, our customer base falls into 8 different industries, everything from aerospace and space exploration to automotive to HVAC and refrigeration to power generation. Effectively, if it is an industry which has a turbo machine in it, we're working with clients in that area. So this slide here, it really shows the evolution of Axtreme as a whole. And what's important to note here is that everything you see on this slide came about due to a client's need or request. For example, AxSlice we developed because we had a client that needed a quick way to export blade geometries and profiling. At the time, there was nothing on the market that was able to effectively do this, so we developed that specific module with them in mind. Another example of this is Axstream Ion. This is our integration and automation platform, and really it helps structure the entire engineering workflow. So tying together not only your conceptual and detailed design tools, but also CAD, CAM software, system level software, advanced CFD tools such as Star CCM and so on. So Axstream is our multidisciplinary design, optimization, and analysis platform for turbomachinery. It can handle everything from preliminary design all the way through CFD, stress analysis, rotor dynamics, and it can handle a number of different configurations, axial, radial, mixed flow turbomachines, compressors, pumps, fans. Again, if it's a turbo machine, Axstream has you covered. What really makes the platform unique, besides the fact that it is the only platform on the market that is fully integrated from preliminary design all the way through to 3D geometry and system level design. But we really place a lot of value on clean sheet design. So through preliminary design and meanline and streamline, we're able to use those tools to develop a feasible design in the early stages. I'm sure, as many of you know, there's nothing worse than getting to the CFD 3D optimization phase of a design and realizing that it's just not going to work. And then having to start from scratch. It can be very costly and it's not super time effective. So our attitude is to get as close to the actual design as you can in the early stages, and then ideally by the time you get to CFD, your design is 90% of the way there, and you just need to make some minor tweaks. So as I mentioned, Axstream, it can handle basically any configuration for a turbo machine, which can be seen here. And Axstream Rotor Dynamics, which is our structural tool, this can handle lateral torsional analysis and model a number of different bearings. So traditional bearings such as rolling bearings, tilting pad oil bearings, gas foils, and so on, but also magnetic bearings, which is going to be the topic of this webinar. And during the case study, you'll see the software pop up a few times as we sort of run through it. So as I mentioned, we still to this day do a number of R&D and engineering projects. It still makes up about 50% of our business. So we can help clients with everything from the initial feasibility study all the way to the complete 3D design. And then we also partner with a number of different manufacturers, so we can really help advise you to take that geometry and those blueprints and turn it into a tangible product, which is really exciting, and definitely it's easier to go through one or two vendors as opposed to sort of a number of different people. So as I mentioned at the beginning of this presentation, we have a number of different classroom training courses. Just due to the global situation right now, our entire curriculum has been taken online. So everything you see here is offered in the form of an online course. We also offer corporate learning programs, which are super tailored to the specific needs of your customers, of your company and your team. And then finally, we have a extensive online self-paced video course platform called STU. So this offers pretty inexpensive courses. They range between $275 to $400 for an entire course, and it includes software in that purchase. And it's a really great way to kind of get your feet wet or brush up on turbomachinery design fundamentals, rotor dynamics fundamentals, if you're sort of limited in both time and budget. This is the last slide before I pass things over to my colleague. But I just wanted to briefly mention our technical support. We have a really strict policy in terms of technical support. So any question which comes in, regardless, you'll hear from us within an hour. Now, of course, if it's a more extensive question, such as details about loss models, or effect of a specific design parameter in your case, it may take us a little bit longer to analyze it. But even those questions are still answered within a business day. And then finally, we also handle feature requests. So if you're using the software and you really need a particular feature and it's not available at the time, we'll really work with you to make sure that we develop that, that feature within the software in order to make sure that the tool is really working for you. All right, so that concludes my spiel. I'm going to pass things off to my colleague, Vladimir, and he is going to take you guys from here with the technical portion of this presentation. So Vladimir, you should have control now.
Thank you, Kim, and hello, everyone. So today we are going to discuss the features of rotor dynamics analysis for turbomachines with active magnetic bearings. Let's start from a brief AMB application and history review. Active magnetic bearings, or shortly AMBs, have been reaching a high popularity among engineers and scientists as support systems for highly speed and low friction machines. They are used for natural gas extraction and transportation systems in compressors, turbo expanders, and expander compressor units, for power industry in steam and gas turbines, for electrical motors, for some specific applications where the other types of bearings are inapplicable, for example, a nuclear ultracentrifuge, an energy storage flywheel, machining spindle, turbomolecular pump, etc. The size range of machines with AMBs varies from very small to big applications with power and speed limits of 30 megawatts and 150,000 RPMs. Very big machines are excluded due to impossibility to implement compact AMB designs for them and other physical limitations. For example, active magnetic bearings were implemented in a pipeline compressor for natural gas transportation with power consumption of 6 megawatts and rotational speed of 9,000 RPM. Gas turbine and generator assembled in 4 radial and 1 thrust bearing producing 9 megawatts of power and rotating at approximately 6,000 RPMs. Another gas turbine engine rotating at 6,094 RPMs. Steam turbine with power of 10 megawatts and rotational speed of 5,400 RPMs. High-speed synchronous motor series with the biggest unit of 30 megawatts and 6,000 RPMs. Turbo expanders with rotational speed up to 40,000 RPMs. And as I said, some special applications like gas cooling gas compressor for a power laser cutting metal sheets with power consumption of 12 kilowatts and rotational speed of 44,000 RPMs. And another example is a 140 kilowatts energy storage flywheel rotating at 36,000 RPMs and providing an uninterrupted power supply for 15 seconds. So, what is the main principle of active magnetic bearing? The main idea of an active magnetic bearing is based on the electromagnetic processes. It works on the principle of electromagnetic suspension based on the induction of eddy currents in a rotating conductor. Electrical currents passing through densely wound copper coils create magnetic fields. This field interacts with a magnetized sleeve connected to the rotor. Here on the figure you can see some components including the rotor itself, magnetic bearings with copper coils, and the rest of the components needed to assemble this type of bearing. Now let's discuss advantages of using AMBs in rotational machines. The levitation of a rotor in AMBs results in a number of their advantages in comparison with the other types of bearings. These advantages are the absence of lubrication, reduced friction and wear, as well as variable stiffness and damping coefficients, which provide smooth passing through the resonances. But these bearings also have some disadvantages. These disadvantages they include the production cost of active magnetic bearings and complexity of operational principles. Both of these obstacles should be overcome by a comprehensive R&D process, which are the main goal of our today's discussion. And let's talk shortly about history. The main obstacle of passive magnetic levitation was formulated by Samuel Earnshaw in 1839. He showed the general instability of a levitated body tended to be attracted to permanent magnets. On the other hand, Beams and Holmes in 1941 defended the patent considering magnetic bearings with stabilization means of electromagnetic nature. This was the beginning of the era of stable magnetic suspensions, including fully active magnetic systems or combined magnetic suspensions with AMBs and permanent magnets. The fully passive magnetic suspensions is still unstable in the wide operational range, excluding some specific examples, bearingless motors. So as you can see on this figure, if we use active magnetic suspension that was previously shown with copper coils and windings, with control system, with its own algorithm, we have stable and controllable suspension. On the other hand, if we add some permanent magnets and exclude some degrees of freedom from a controllable part, we still can have stable and controllable magnetic suspension. The passive magnetic bearings with permanent magnets and only with them are in general unstable and what is worse, uncontrollable. Controllability is one of the main advantages of active magnetic bearings. Dr. Beams developed the first practical magnetic suspension for high-speed rotating devices in 1940s-1950s. Further studies were performed by SEP and NASA. The advances in solid-state electronics and modern computer-based technology of Kabermann and Schweitzer in the late 1970s gave the fresh breath to the AMB developments. The company S2M, formed by SEP and SKF in 1976, was the first to commercially market active magnetic bearings. All this became possible when the appropriate control systems arrived. So it occurred in the late 1970s. So what are the operating principles of active magnetic bearings, AMBs? The comprehensive studies in the early stage of the AMB development indicated the following points regarding active magnetic bearings. Electromagnets enable change in magnetic field parameters by varying the current in the copper coils. The adequate variation of electromagnetic field requires using a certain control law. The control law should be designed properly and ensured by the control system. Magnetic suspension can include permanent magnets if at least one active magnetic bearing is introduced in the system. The AMB control system operation includes the following steps. A sensor measures the displacement of the rotor from its reference position. A microprocessor, as a controller, derives a control signal from the measurements. A power amplifier transforms this control signal into a control current. The control current generates a magnetic field in the actuating magnet. This results in magnetic forces which hold the rotor in its governing position, and also the controllability allows us to change stiffness and damping parameters of these types of bearings. The control law of the feedback is responsible for the stability of the hovering state as well as the stiffness and damping of such a suspension. Stiffness and damping can be varied widely within physical limits and can be adjusted to technical requirements. They can also be changed during operation. The complex structure of active magnetic bearings causes the various failure modes inherent in them. AMBs are usually equipped with backup, in other words, touchdown or catch ball bearings. This provides the rotor runout in the case when the control system fails due to instability or electricity issues. And now let's take a look at the newest capabilities of AMB simulations in extreme rotor dynamics. But first, let's discuss the background of such simulations. So what is a specific problem of active magnetic bearings and why does it arise? The problem arises without ensuring the stability of a rotor motion in active magnetic bearings. It leads to permanent touchdowns to backup bearings and as a result abrupt change of critical speeds with increased and balanced response vibrations. After the touchdown, the rotor is recommissioned, and while the new instability issue occurs. So here we have the loop process of reinstallation of the rotor, but this loop process results in an accumulated damage of the rotor. Reaching the critical damage of the rotor causes its failure. But all these issues can be avoided by an appropriate tuning of the AMB control system and optimal choice of AMB parameters with ensured stability of the rotor motion. These analyses are now available in extreme rotor dynamics, with all the necessary algorithms built into the solver. So with proper choice of AMB component parameters, we can eliminate these touchdowns, these problems at all, and we can make our rotor to levitate without any problems or issues. And this is possible now with extreme rotor dynamics. It is based on several standards. First, ISO standard. Evaluation of the safe operation of rotors in AMBs is standardized by ISO 14839, available in 4 parts, which you can see in this slide. It was developed by the expertise representatives of AMB manufacturers and research universities. The detailed requirements applied to axial and centrifugal compressors and expander compressor units are discussed in the Annex E of the 8th edition of API 617. ISO 14839 introduces sensitivity function as a new method to evaluate the stability merging of the AMB system with 4 zones as criteria of rotor stable operation. So here on the picture, on the figure, you can see 4 zones on the sensitivity function plot, which will be discussed later during this presentation. Here you can see these zones, and to ensure the 100% stability of a rotor in AMBs, we need to make our rotor be underneath the A-B limitation, namely 9.5 decibels. Extreme rotor dynamics allows users to create conceptual designs for active magnetic bearings of a rotor by satisfying ISO and API standard criteria for AMB rotor systems. As an input information, we need to apply initial parameters of AMB components and rotor geometrical model. Then, the control system simulation in extreme rotor dynamics indicates whether all the limits for the rotor safe operation are acceptable. It may require additional steps or additional iterations to define the optimal AMB parameters. After that, these parameters form the AMB conceptual design ready for implementation. And what is the advantage of this method is that the parameters which are input into extreme rotor dynamics reflects the real parameters which we need to apply to our AMB design. So when we, after this iterative process, when we knew the optimal parameters of AMB defined by extreme rotor dynamics, we can already implement them into conceptual design. So this is the big advantage of extreme rotor dynamics. The built-in algorithm of extreme rotor dynamics corresponds to the ISO and API requirements and allows users to perform preliminary stage of AMB design, simulation of control system operation, lots of transfer function, sensitivity function, and Nyquist diagram with further evaluation of stability condition. The rest of lateral rotor dynamics analysis, which are being implemented in the extreme rotor dynamics module. Evaluating the stability of rotors in AMBs is a challenging task in terms of mathematical modeling. The complex calculation scheme was introduced in extreme rotor dynamics. You can see the very simplified model of this scheme on this slide, and believe me that each of these squares contain a lot of mathematics, which is intended to deliver the most accurate modeling of active magnetic bearing control system operation and reflects its stability and rotor dynamics overall. And today we are going to focus on the stability evaluation procedure in this module in extreme rotor dynamics. So let's consider the real case of 5-stage compressor with AMBs taken from the published source. It is the real application installed in the Groningen natural gas field, which is located in the northern part of the Netherlands. The brief you also can see the machine parameters on this slide. It's quite a big machine, and it is installed in AMBs, which delivers better friction properties and controllable stiffness and damping parameters. And the brief sequence of actions for analyzing it is as follows. First, we need to build the equivalent beam model of the rotor, including mass and stiffness diameters of sections and point mass elements as in any other rotor dynamics analysis. Here you can see the drawing of this machine and this simplified equivalent beam finite element model with added masses and stiffness elements. And here is the input. Extreme rotor dynamics allows users to build beam and plane axisymmetric finite element models and perform all the types of torsional and lateral rotor dynamics analysis required by API standards. After that, when we have our finite element beam model, we apply the parameters of actuators defining their geometrical and physical properties without applying the target stiffness value. Controller properties containing the form of the control law. Filter properties tracing for the unstable frequency range, as well as sensor physical properties. All these form the closed scheme of AMB parameters that are extreme rotor dynamics models in its solver, and it reflects the structure and design of real active magnetic bearing designs. Then we built the assemblies of active magnetic bearings. For the considered case, we have the rotor installed in 2 radial active magnetic bearings. We specify the 2 assemblies with actuators and sensors related to the corresponding rotor section. We also specify which models of actuators and sensors should be used for each assembly. Here we have the only one model of actuator and the only one model of sensor, but it can be included into several active magnetic bearings. But we need to specify where is actuator located for a certain AMB and where is a sensor located. Also, we specify controller and filter models. After that, we need to perform critical speed map analysis and define the reference target stiffness. This reference target stiffness is then applied to the actuator properties. This is not the actual stiffness of active magnetic bearing. The actual stiffness is controlled by control system, but we need some reference value which allows us to eliminate a lot of resonances, to have such point on our critical speed map which is free of resonances in terms of the operational speed range. And then we initialize the solution process. After initializing the solution, the internal AMB simulation algorithm starts working. It performs background lateral natural frequency analysis of rotor without any bearings, so-called free-to-free analysis. Here you can see the forms of this analysis defined by critical speed analysis, but to simplify the modeling process, it now is working in the background by simulating the active magnetic bearings. The mathematical modeling within the built-in extreme rotor dynamics algorithm simulate the following. Power amplifiers convert controller-specified voltage into magnetic actuative fields. Radial electromagnets convert amplifiers-driven field into rotor forces. The rotor converts applied forces into physical displacement and velocities. Sensor convert physical displacements into voltage. Anti-aliasing filters condition the tensor signal before they are sampled by a digital controller. Digital controller hardware introduces sampling delays. As I previously said, it is a real physical process that takes place in the AMBs, but it is simulated by extreme rotor dynamics, and this makes our model the most accurate as possible. Then Laplace transformation enables calculation of the complex frequency-dependent AMB transfer function, its representation in the form of Nyquist diagram and sensitivity function plot for stability evaluation according to ISO standard. As a result, the extreme rotor dynamics provides users with additional plots to analyze the stability of the rotor motion in active magnetic bearings. Observing the sensitivity function plots allows users to define to which zone the rotor belongs according to ISO requirements. As you remember this from standard slide, we need to have our rotor in the zone A to make sure it is 100% stable. So peak values of sensitivity functions lower than 9.5 decibels correspond to fully stable rotor motion. And at the next step, the unbalanced response of the rotor in AMBs should be calculated to determine the actual values, peak values of displacements during its vibrations. And now we will discuss a brief software demonstration. Let's consider the simpler example of a symmetric rotor with 2 disks for software demonstration. So now let's have a brief look to our software. Here our extreme rotor dynamics module, and it has a project tree view where, as I said, we have the rotors, we can build the models of rotors, we can specify bearings, and as in particular active magnetic bearings. We can also add supports since they influence the vibrational properties of rotors also significantly. And we can make the assemblies of some rotors. In particular, we can make the AMB assembly here. I will explain it later. And we have some solutions for axial, lateral, and torsional vibrations. Today's point of view is lateral vibrations. We also can specify some materials here. So first, to model the considered case, we need to build our rotors. I've already done this to save some time because maybe we are running out of time. So here we have some components of our rotor. We have shaft consisting of some stations with lengths and diameters, stiffness and mass diameters. We have 2 impellers, left and right. We have active magnetic bearing sleeve in the left and in the right. And also we have an electrical motor, the rotational part of an electrical motor which is installed on the rotor. Then we need to assemble our system. Here you can see our assembly, which is consistent with the drawing that we've seen in the previous slide. Here we specify some couplings to have our model assembled properly, and then we can model active magnetic bearings. Here, as in the previous example, we have the only one model for actuator with some input parameters, one model for controller with its own input parameters, which are coefficients of the corresponding control law, some parameters for filters, and some parameters for sensors. So here we are modeling the properties of active magnetic bearings components, but then we can do our A and B assembly, where we specify how active magnetic bearings interact with the rotor itself. Here, as we mentioned, we have two radial magnetic bearings. So we have two lines here that are pointing to actuator model, to sensor model, to controller model, and to filter model. Also, we need to choose the rotor to which belong the actuator and station. Here it is sleeve left, it's our A and B sleeve, and station 2, this station. So here we have our actuator installed of the left A and B. The same for sensor. We need to specify the sensor rotor and sensor station. And here, as you can see, we are specified it on the shaft and at the station 3. The same was done for the right bearing, where the actuator is located here, the sensor is located here, and also we use the same models of actuator, sensor, controller, and filter for the right active magnetic bearings. And these lines form the channels. We have two channels for corresponding to two active magnetic bearings, which I will refer to this later. So after that, we can implement some analysis. The first and foremost, in any rotor, not only for rotors in active magnetic bearings, we can implement static gravity analysis to define some deflection forms of our rotor. Here we can see the deflection of our rotor and reactions, as well as some tensile, shear, stresses, bending moment, shear force, axial force, which are used for different criteria on defining the static strengths of our rotor. But it is a general for each rotor, not only in AMBs. Also, we can define some critical speeds of fixed rotor, and you can see critical speeds and critical modes corresponded to the rotor. Also, it is general analysis, but as I said, the first analysis of interest is our critical speed map analysis. In this analysis, we can define the target stiffness that delivers the most of absence of resonances in our system. Here we can enter some value where the list of resonances can occur and where the critical speeds are much far from the operational speed range, which is shown here. But we also define this target stiffness. We defined it and we can enter it here into actuator properties. This will be the reference point for further simulations. So here what critical speed map analysis says to us, and then we do the stability analysis. We have some general tabs here regarding damping coefficients, Campbell diagrams, rotor response. All this is standardized by API standards, and this should be analyzed during rotor dynamics analysis of any rotor, not especially in AMBs. But here is the plot of interest. Here we have amplitude pace characteristics, Nyquist plot, and sensitivity function, the most interesting part, because this part allows us to define whether our rotor in active magnetic bearings is stable or not according to ISO standards. We also see here two channels. As I told you, we have two AMB assemblies, here, and each AMB assembly corresponds to its own channel. So here we have these channels, and we can observe, for example, sensitivity function for the second channel, for the first channel, or for both of them. And then we can also perform unbalanced response analysis, which shows us some amplitude frequency characteristic and tells us some actual displacements of rotor during its vibrations. So this is a brief scheme of this analysis of rotor in active magnetic bearings. And what we can conclude here. Using effective magnetic bearings for turbomachines provide many benefits, such as absence of lubrication, reduced friction and wear, capability to control and vary stiffness and damping coefficients, which ensure smooth passing through the resonances. Due to the complexity of AMB rotor systems, a comprehensive simulation of their motions, considering properties of all their components, is required. Extreme rotor dynamics introduces integrated capability to simulate all the components of active magnetic bearings and check the stability of the rotor and AMB system motion according to the latest ISO and API standards. Extreme rotor dynamics enables analysis of existing AMB units and synthesis of new AMB structures due to the detailed modeling of all the components of active magnetic bearings. Performing an interactive simulation in extreme rotor dynamics allows users to design AMB units which ensure stability of the rotor motion and are ready for implementation in new rotating systems, can replace less efficient fluid film bearings in existing rotating systems. Thank you for your kind attention, dear colleagues.
All right. Thank you, Vladimir. We did have a bunch of questions come in. The first one that I have here is, as a rule, most bearings, such as fluid film, rolling element, are modeled as spring damper elements for rotor dynamics analysis. Can we consider active magnetic bearing calculations in the same way?
Oh, thank you, Kim. It's a very interesting question. Because of course we can do it, but it will be too simplified approach. Because as I tried to show you, the dynamics of rotors at AMBs is particularly frequency dependent, and to take these features into account, we need to simulate control system operation. But this is impossible by simply applying spring damper elements in bearing locations. And in contrast to a number of engineering codes, extreme rotor dynamics simulate the problem in a general formulation, and like it is similar. You saw that we need to apply a lot, huge number of values, a huge number of parameters here in the module to model our active magnetic bearing. But if we apply this simplified approach, we need to only apply stiffness and damping characteristics, which are much less values than these parameters, and you can imagine how simplified this approach is. So,
Right. Thank you. The next question that I have here is, does active magnetic bearings require perfectly balanced rotors? Can active magnetic bearings be used for rotor balance ISO 1940 G2.5 or G1?
oh, thank you for this question. Yes, AMB can be used for rotors balanced according to ISO 1940 grades, G2.5 or G1. A rotor can be perfectly balanced, at least in a real life. So, an AMB control system allows operation with such types of balancing grade, of course, if the AMB system is properly designed.
Okay, perfect. The next question I have here, can the rotor with fluid film bearings be reinstalled in active magnetic bearings, and what do we need to do if yes?
It's also interesting question. To have a definite answer on this question, we need to perform various rotor dynamics calculations using extreme rotor dynamics. We can simulate fluid film bearings in the bearing module, then simulate the dynamics of a rotor in them and perform similar simulations for active magnetic bearings in the rotor dynamics module with varying AMB parameters. Comparison of these results will show if the usage of active magnetic bearings is reasonable for this specific rotor. It may happen that it is in some cases it is like unphysical, but in the most of cases it is applicable, but we need to have the parameters, and extreme rotor dynamics should help us to have these parameters, optimal parameters for such the system.
Perfect. The next question I have here is, what type of controller is used for active magnetic bearings? Is it PID controller?
Yes, at the present moment in extreme rotor dynamics, we have capability to simulate and design a PID controller, but in future we plan to extend capability for other types based on client needs.
Perfect. The next question I have here, Softenway has the standalone module for bearing calculations. Why are active magnetic bearings simulated in the module for rotor dynamics calculations?
Thank you. You know, the rule of thumb for fluid film and rolling element bearings is to calculate reactions in bearings by static gravity analysis, then apply them during bearing calculations, define the stiffness and damping characteristics, either frequency dependent or not, and specify them during rotor dynamics calculations. This is similar to what I explained during my previous answers, that we can specify this using just bearings. We can specify some stiffness and damping parameters of these bearings. They can be frequency dependent, but An active magnetic bearing is a mechatronic system with interconnected mechanical and electromagnetic processes. To account all of these features, we need to simulate the rotor in an AMB system using one complex mathematical model. But that's why the AMB simulations are integrated with the rotor dynamics module. It's like a very, very close interaction, and we cannot divide these parts.
Perfect. The next question I have here is, what is the number of bearings used? Or how much number of bearings is used? I
In
think
our case, in our specific case, we have two bearings. In software, we can simulate any number. I think we can ask the client, or we can interact with the person who asks. It can be any number, and we can simulate any number. For example, as I said, I'll maybe show you. 1 second, please. Is something in the top, but here we have 4 radial active magnetic bearings in the powertrain. So we can model if the coupling is stiff to that limits us to model all powertrain. We can model it with 4 active magnetic bearings. It depends in general.
All right, thank you. Then the next question I have here is, which type of active magnetic bearing controllers can be modeled in extreme rotor dynamics?
Now, the current version of our module introduces the SISO, single input, single output controller. The MIMO, multiple input, multiple output controllers are in the process of development, and they will be introduced.
Okay, thank you. Next question I have here is, how are we defining the targeted stiffness for active magnetic bearings?
Thank you for this question. I tried to say it maybe not clearly. The target stiffness should be selected to avoid resonance conditions based on critical speed map analysis. Okay, I show you maybe. Okay, in the slides here. Oh, here we have. So, first condition, it should correspond, should be consistent with our actuator model, because if we have like big actuators, or we have very tiny actuators, depending on the machine, the tiny actuators cannot produce the huge stiffness. So we are limited here by this, and we are limited by these physical meanings, and at the same time we should see that we have no any resonances. Like here we have the lines showing the operational speed range here. So if our stiffness is something here, we are in resonance, because it will intersect our lines showing critical speeds. Dependence on bearing stiffness will intersect our operational speed range. So we are here in resonance. So we choose some target stiffness far from this points, but at the same time we choose it properly to reflect our actuators. Like it is a process of maybe some creative process.
Thank you. The next question I have here is, could you please describe the approach to control system simulation?
Yes, of course, it is. I mentioned previously that extreme rotor dynamics use the control system with PID proportional integral derivative controller and notch filters. This is the most common scheme, and it is introduced in extreme rotary dynamics, and it represents all this. It is represented by all these parameters which are in the input of our module, extreme rotary dynamics.
All right, thank you. I think this is going to be the last question we have time for. Is ISO standards applicable to all types of machines and active magnetic bearings?
Thank you for the question. ISO 14839 considers active magnetic bearings as mechatronic system with input of the parameters of their components and rotor vibrational properties. So it can be applied to any rotor in general. Another question is the applicability of active magnetic bearings to a certain machine. It should be ensured by considering the ISO standard for this case. And the rotor dynamics analysis of the rotor and AMB system and extreme rotor dynamics is based on both ISO and API standards, which will answer this question.
All right, thank you. And just a note to the audience, I do see a number of other questions that are that have come in. So for anything we didn't get to today, you'll be hearing from our team within the next 24 hours to answer all of these different questions here. And thank you so much for all of the questions that came in. Thank you, Vladimir, for going through all of this, and again, thank you everybody for joining. The last thing that I want to point out is if you think of any other questions, definitely feel free to reach out to us via email. We'll see anything that comes in, so you can just email us at info@softenway.com. But otherwise, thank you again for taking the time to sit in with us. We hope you enjoyed it, and have a great rest of your week.
Thank you, everyone.
All right.
Bye.